there's a formula we can use, okay? We would do the probability of A or B, okay? The or, by the way, is it's an and or a, it's not. So in English, there's this ambiguity when I use the word or. If I say, I can ask you the question, do you like vanilla or chocolate ice cream? You can say, I prefer chocolate, or I prefer vanilla. In statistics, or I guess computer science, you would answer that with a yes or a no. Do you like vanilla or chocolate ice cream? You would say yes, or no, I don't like vanilla or chocolate. Because what we were saying is that if it satisfies A, then it counts. Or if it satisfies B, it counts. Or if it satisfies both, it counts. So it is not a choice. It's not one or the other, meaning but not the other. It's A or B or both. Okay, so or is A or B or both. So when I say the probability of A or B, this is equal to the probability of A plus the probability of B minus any possible overlap, A and B. Okay. So if I say, what's the probability that a card, a randomly chosen card, is a face card or a heart, we would do the probability of face card or heart. And by way of formula, we would say this is equal to the probability of getting a face card plus the probability of getting a heart minus probability of getting a face card and a heart. So we already calculated the probability of drawing a face card, and what was that probability? 12 out of 52. What is the probability of drawing a heart?
13.
13 out of 52, or 1 out of 4. Okay. And if I were to just stop right here, my answer would be wrong. And why would it be wrong? Because there's overlap. I am double counting the face cards that are hearts. This 12 out of 52, there's 12 cards here, and there you are, the Jack, Queen, King of hearts, clubs, spades, and diamonds. Okay. And these 13 out of 52, these are the, ace all the way up through king of hearts. So the Jack, Queen, and King of hearts show up here, and they show up over here. Okay? So we want to just get rid of one of those sets. Not both of them, but just one. And so I'm going to take out the heart card, the face cards that are hearts. And how many of those are there? 3. So the probability of that would be 3 out of 52. So my overall probability would be 22 out of 52. Probability of drawing a face card or a heart. Acceptable? Okay. Sometimes we have a situation where there is no overlap. Okay? So what if I ask, what is the probability of drawing a heart or a black card? This would equal what? card is both heart and black. And what is the answer here? This is 1 out of 4 plus 1 out of 2 minus 0. So there's no overlap. There are no cards in the deck that are both heart and black. By definition, heart cards are red cards. So there are no cards that are both heart and black, and so we have no overlap, so we subtract out 0. Okay. So apparently this is a common enough situation where we give it its own rule, but it's really just a special case of the OR rule. So we'll say if A and B are mutually exclusive, or also known as disjoint, that means probability of A and B equals 0. And so for mutually exclusive A and B, then the probability of A or B is equal to the probability of A plus the probability of B. Because the overlap is 0. But it's just a special case of the general OR rule. What about then we have conditional probabilities and ands, okay? So we might have a question what is the probability of A and B? Sometimes, or so far in our example with dealing with a deck of cards, we just think about the deck of cards and we ask, well, how many cards satisfy A and B? So if I said, what's the probability that a card is both face card and red, or face card and a heart, you can just think in your head, how many cards in the deck are red and, are face cards and hearts or whatever, and you list them off in your head. But this might not always be possible. We might not know the individual elements in our data or the situation that we're speaking of, okay? So we could have a situation with conditional probabilities, okay? So probability of A and B, I'm going to just write out what this is equal to. This is equal to the probability of A times the probability of B given A. All right, this is written or read as probability of B given A. Okay. And the labels of A and B are arbitrary. So this is also equal to the probability of B times the probability of A given B. But don't mix pieces of this one up with pieces of this one. You're going to put probability of A here to the probability, you multiply that by the probability of B given A. Alright, so what does that mean? This could be something like, the probability of a thunderstorm is 30%. So let's say there's a 30% chance of a thunderstorm. So I would write this as probability of thunder, as short for thunderstorm, as 0.3. And I could say, if there's a thunderstorm, the probability that my flight is delayed is 70%. So how would I write this in terms of an equation? I would write probability of delay. So the probability that a flight is delayed given, or if there is a thunderstorm, is equal to 0.7. It's important that we write thunder after the vertical bar, because that is how this sentence is written. It's saying, if there is thunder, or given the fact that there is a thunderstorm, then the probability that there's a delay is 0.7. If you were to write it the other way, saying probability of thunder given delay, that's saying, what's the probability of a thunderstorm if the flight happens to be delayed? It sounds a little odd, but it's a valid question, but it's written different. On the other hand, if there is no thunderstorm, then the probability that the flight is delayed is only 10%. And so this would be the probability of delay given what? Yeah. No thunderstorm is equal to 0.1. Okay, so some questions. I don't know if it's too hard. Okay, so you guys have that, right? Probability of A and B is equal to the probability of A times the probability of B given A, all right? And again, A and B, the labels are arbitrary. So if we wanted to call the first thing B and the second one A, that's also fine. So based on this information here, what is the probability that there is a thunderstorm and my flight is delayed? Well, don't shout out your answer. Think of your answer. See if you can do the math here. All right, do we have an answer?
1, 2, 1.
So the answer is 0.21. Okay, so this would be the probability of thunder and a delay. So this would be the probability of thunder times the probability of delay given thunder. So there is a 0.3 chance of a thunderstorm, and if there is a thunderstorm, if that does come to realize, then the probability that my flight is delayed is 0.7. So an overall probability of thunder and delay to be 0.21. What if I ask, what is the probability of a thunderstorm and no delay? So what's the probability that a thunderstorm happens, but I still manage to get an on-time flight?
30.
So this would be probability of thunder and no delay. So that would be probability of thunder times the probability of no delay given thunder. Alright, probability of a thunderstorm is 0.3. Do we know what the probability of no delay given a thunderstorm? Yeah, so we have the probability of a delay given a thunderstorm is 0.7. So that means if there is a thunderstorm, the probability that my flight is delayed is 0.7. But if there's a thunderstorm, the probability that I manage to get by with no delay would be 0.3. So then I'd have 0.3 times 0.3, and I would have 0.09. Is that good? All right. So let's try one more, and then. So what is the probability of no storm and no delay? So this is what we want. We don't want a storm. We don't want to be delayed. .63. That's what I'm getting. Okay. So this would be probability of no storm times the probability of what? No delay given no storm. Is that okay? All right. And so if the probability of a storm is 0.3, then the probability of no storm is 0.7. And the probability of a delay when there's no thunder is 0.1. So it's the probability of no delay when there's no thunder. 0.9. Okay. And that's how we get 0.63.
It's a really good airline.
What's that?
It's a really good airline.
Is that a good airline?
Only 10%.
10% delays with no storms? Yeah, I guess it depends who you are and how often you fly. All right, we can illustrate a lot of these things with what we call a probability tree. And so all of these things that we did can also be drawn with a probability tree. Okay, so I can say, you know, what's the probability, if I ask the question, what's the probability that my flight gets delayed overall, whether or not there's a storm? What is that question? It's a little bit difficult to answer, but we can answer it easily. Or I don't know, I think it makes it easier when we use a probability tree. Okay? And so this lists out the possible way things can unfold. Alright. So when the day starts out, there could either be a thunderstorm or there might not be one. And if there is a thunderstorm, your flight might be delayed, or it might not be. And then if there's no storm, it might be delayed, and it might not be. What did we say the probability of a thunderstorm was? 0.3, okay? So right here I'm going to write 0.3 along this branch to indicate the probability of a thunderstorm. So right here I write probability of thunder gives me 0.3. Over here I would write 0.7 because the probability of no storm is 0.7. What number goes along this branch? This says, now that we know that a thunderstorm has happened, what's the probability that I get delayed? Yeah, we said this is 0.7. So technically, so this number is probability of a delay given a storm. And I apologize that my writing is inconsistent because I'm sometimes writing thunder and sometimes writing storm. I hope that's not too confusing in your notes. Okay, so probability of a delay given a thunderstorm, 0.7, which means the probability that there is no delay is 0.3. On the other hand, if there's no storm, what's the probability that we're still delayed? 0.1, and over here I would then have 0.9. And so when we multiply down the branches of our probability tree, we get the answers to our AND questions. So what is the probability of a thunderstorm and delay? We got 0.21. What's the probability of a thunderstorm and no delay? 0.09, 0.3 times 0.3. What's the probability of no storm but still being delayed? 0.7 times 0.1, 0.07. And probability of no storm and no delay gives me 0.63. Is that okay? So we can also label each of these as probability of no storm and delay, or however we need to. It's very important that we can distinguish between delay and thunderstorm versus delay given thunderstorm. Are we okay with that? Alright. So I've already erased it. But the probability of a delay given a thunderstorm is 0.7, but the probability of a delay and a thunderstorm is 0.21. There's a very important and major difference between the given probability, or the conditional probability, and then the and probability. Okay, so if we have this probability tree to guide us, we can ask, what is the probability that we experience a delay? So this is just, what's the probability that we experience a delay overall? Including the times when there is a thunderstorm, including the times when there is no thunderstorm. Okay, so this is made up of, there's two possible ways that we can end up with a delay. One is the probability that there is a thunderstorm and there's a delay, plus the probability of no thunderstorm and there's still a delay. Okay. I guess I should say, well, it's this event or this event, and then these two, can we see that these are mutually exclusive? We cannot be in a world where there is a thunderstorm and a delay at the same time as there being no thunderstorm and a delay. Okay. So because of that, there's no overlap for us to subtract. So I just add these two together, and I have 0.21 plus 0.07. The overall probability of the delay is 0.28. Is that okay? All right. So what if you go to the airport to pick up your friend, okay? And your friend just said, I don't know, for some mysterious reason, decided to send you all of this information. Probability of delay, because if there is a thunderstorm, is point this, and probability of a thunderstorm to begin with is this and that. So they give you all of this stuff, and then you get to the airport, you look at the logs, and it says, flight whatever is delayed. So you say, oh, I wonder if there was a thunderstorm. Okay. So, if a flight is delayed, what is the probability that there was a thunderstorm? How do we answer this? Okay, this, if I wanted to write as a probability thing, this would be written as what? Probability of a thunderstorm given a delay. Alright, so notice this is different than probability of delay given a thunderstorm. This time, we know the given piece of information is that there has been a delay. And now what we are wondering is, was there a thunderstorm or not? Okay. So how can we answer this?
Divide 0.21 by 0.28.
Yes, okay. So, if we look at our tree, we've established that the overall probability of there being a delay is 0.28, right? We figured that out. And if we know that there has been a delay, our universe is now limited to either this scenario or this scenario, right? There's been a delay, so we either ended up delayed over here where there was no thunderstorm, or we ended up delayed when there was a thunderstorm. Okay. And so, we want to know, what is the probability that there was a thunderstorm? So, in our world, we're limited to just those times when there was a delay, and that happens 0.28 of the time. And out of that, we can end up with a delay when there was no thunderstorm. That happens 0.07 of the time. And we can end up with a delay when there is a thunderstorm. That happens 0.21 of the time. So I would do 0.21 divided by 0.28. And this gives me 0.75. So if there has been a delay, what's the probability that there was a thunderstorm? I would do 0.21 divided by 0.28, and that is equal to 0.75. Is that totally confusing, or does that kind of make sense? Who's lost? Anyone lost? Here, we'll try an example just to make sure we understand this. All right. So let me just put kind of the general formula form of this. All right. So thunder given delay. So oops, this is not what I want to do. Anytime you have a probability of A given B, or B given A, whatever, however it's written, okay? If you're asking what's the probability of A given B, this is equal to the probability of A and B divided by the probability of B, okay? And in our case, B was the delay, and we found the overall probability of a delay earlier when we added these two together. And then the probability of A and B, or thunderstorm and delay, we've established with earlier in the tree as 0.21. All right, so shall we try this an example problem out to make sure you guys understand this? All right, we'll try this, and I hope this works. And then we'll take a short break. Okay, so let's say there is, if we pick a random person, so let's say if we pick a random person, there is a, let's say, 1% chance, or 1% probability that a randomly selected person has the mutant gene. Alright, so anyone see X-Men Days of Future Past? Well, anyway, so this is just some made up thing. Alright, so let's say there's a 1% chance that someone has the mutant gene, right? And then Trask Industries, they said they have this device that can hone in on the mutant gene, detect whether someone has the gene or not. Now in the movie they promised that it was super accurate, but let's say that's not the case, all right? So if someone does have the mutant gene, let's say there is a 95% chance he is detected. Detected by, I don't know, Trask's device, all right? But there might be a problem, and maybe it sets up false alarms also. So even if someone does not have the gene, let's say there is an 8% chance that the device quote-unquote detects as mutant. So, a false alarm. Alright. Okay, so let's say someone is reported or detected by the device, okay? What is the probability that this person actually carries the mutant gene? Okay, go ahead and try that out. Does the question make sense, first of all, before I let you guys try this? Okay. If there's any questions, raise your hand. Let's see if you can do this.